pH of acids and bases. So in the pH scale, when we're talking about acids and bases, we're going to always use it in terms of pH. And pH is going to be less than 7 is going to be an acid. So pH of less than 7 is going to be an acid. So right here, less than 7 is an acid. If a pH is greater than 7, it's a base, so that says alkaline, but we'll say a base. And then, of course, if you're exactly 7, you're neutral. Okay, we will always use pH to determine the acidity, or if it's a base. We're going to talk about something called pOH in a minute, but we never use that to determine if something's an acid or a base when we say pH. So here's just some common items of everyday use that you can see that are acids or bases. Things like fruit are acidic, stomach acid is very acidic, and then things like your cleaners like soap and bleach and oven cleaner are going to be basic. And then pure water, and when we say pure water, we mean nothing in it, it's just hydrogen and a hydroxide, H2O, it's going to be neutral. So the pH scale is going to indicate the hydrogen concentration. And whenever we're looking at this, we're going to see that we can represent that as H or H3O plus. Okay, we're looking at the dissociation of water, so it can either form an. Sometimes I'll show you in a minute. It'll either show it as H or H plus or H3O plus. It kind of just depends. Like if we're showing the breakdown of water by itself, we would say H plus plus OH minus. But then sometimes if we're saying we have water plus water, what we really end up getting is H3O plus plus the OH minus. This is technically the correct way, the H3O plus, but a lot of time you'll see it this way instead because it's easier to write and it kind of basically means the same thing. So the way we calculate the pH is we take the negative log of the hydrogen concentration. And let me backtrack a little bit and show you that when something's in a bracket, it means concentration. So we want the concentration of the hydrogen, we take the negative log. When you're typing that in your calculator, you make sure you use the negative sign and not the minus sign because it'll give you a wrong number. Now, if we have pH and we want to find the hydrogen concentration, we can take 10 raised to the negative pH, which is also the antilog. And you can, when you're plugging that into a calculator, you can either do 10 raised to the negative pH, or if you do this inverse function on your calculator of the log button, it's also 10 raised to the x, and then you would type in the negative pH. When we're talking about the pH scale, it goes from 0 to 14. 7 is, of course, neutral. Remember, less than 7 is an acid, excuse me, and greater than 7 is a base. We can also find hydroxide. The pOH is the negative exponent of the hydroxide concentration. So we would get the negative log of the hydroxide would give us a pOH. And then, of course, same thing, if we were trying to find the hydroxide concentration and we had the pOH, we would take 10 raised to the negative pOH. Together, pH plus pOH is equal to 14. That's going to be very important. Because if we know one of these things, we can find the other three components. And so we'll show you an example right here. Okay, so if I have a pH of 2, okay, that means that my pOH would be 14 minus 2, so my pOH would be 12. And then if I wanted to take and find the hydroxide concentration, I would say 10 raised to the negative pOH, or it would be 10 raised to the negative 12. Okay, if I had wanted to find the hydrogen concentration, it would be 10 raised to the negative 2. So that's how that would work. Now, a special note about significant figures. They're a little bit different whenever we're calculating them for pH. Okay, so what comes after the decimal is what counts as a significant figure if I have a pH or a pOH. So if I had this value right here, the only two that I would count is 0.1. And that's because pH is on a log scale of 10. And so it would have 2. If I had 12.0, it would have 1. This is only for pH and pOH only, so don't let it confuse you. And we'll practice that as we go through and do a couple of calculations. Okay? So I'm going to do a couple of these. If I was to want to calculate the pH for this first one, I have 0.1 molar HCl. Well, my hydrogen concentration is going to be 0.1 molar. And that's because when that HCl breaks apart, HCl would break apart to form a H plus and a Cl minus. And remember when we did this, we have 0.1, and then this would be 0.1, and this would also be 0.1. But we don't care about the chlorine, it's a spectator. So in order to find the pH, we would take the negative log of 0.1, and we would get 1. Okay? But because this has one significant figure, we would actually report that as the pH is equal to 1.0, because we need one significant figure. If I was to do this next one, I have, this is going to be my concentration because it's given it to me. Okay, so it's going to be 4.0 times 10 to the negative 3. In order to get that, I would take the negative log of 4.0 times 10 to the negative 3. And when I get that value, remember to do negative log, not minus. Negative log 4.0 times 10 to the negative 3. Whoops, got something wrong in my calculator. Negative log. And I get an answer of 2.3979. I have two significant figures here, so my pH would be reported as 2.40. Okay? And then number 3 and 4 are going to be the same. I want to do same, and then for POH it's going to be 5.2. So this time I want to find the hydroxide concentration. So I would say 10 raised to the negative 5.12, and I would enter 10 raised to the negative 5.12, and I get 7.585 times 10 to the negative 5. This has two significant figures right there, so I would report that as 7.6 times 10 to the negative 5th, and then of course the concentration would be M. Forgot that M up there, and that would be my answer. Okay? So where we need to be careful of is if we're finding a base and it asks us to find the pH. So we're going to look at an example of that. Let me add a little paper in here. So one of the things that will show up is, let's say I have 0.25 molar NaOH. Okay, and it says find pH and hydrogen concentration. Okay, so hydroxides are bases. It's a group 1 metal, and so it's a strong base. So if I take the negative log of this concentration, 0.25, it is going to be POH that I'm finding, because it is a base. And so that would come out to be, and that's two significant figures, so I would write that as 0.60 is my POH. And so remember that pH plus POH is equal to 14, and so my pH would be 14 minus 0.6, which would be 13.4. And I would have to say 13.40 because I need two significant figures. And so that would be my pH. And then to find the hydrogen concentration, I would say 10 raised to the negative 13.4. So 10 raised to the negative 13.4. And I would get, needing two significant figures, comes out to 3.981 times 10 to the negative 14. So my final concentration with the correct number of sig figs, which is 2, would be 4.0 times 10 to the negative 14 molar. So that's how you would do that if you start with a hydroxide and you need to find pH. That is a big hurdle. A lot of times people will just say, oh, it's pH because I took the negative log. But if it's a base, what you're finding is POH when you take the negative log. Okay? So let's move on to buffers. oops, I went too far. Let's go back. Buffer is something that occurs when you have things that resist a change in pH. All right, and we call these things buffers. There are a lot of buffers in your living systems, and in English, the word just means to lessen the shock or protect from damaging impact. In chemistry, it means it resists the changes from an acid or base. So for a buffer to work, it must be able to resist an acid or a base. In other words, so the change in pH won't be as drastic. And it happens when you have a weak acid or base added to the salt if it's conjugate, okay? And so we won't be dealing with them as far as calculations. If you go on to take AP Chem, we will, but in here, we'll just kind of need to know what they are. And this is kind of showing you how it works through this process. So feel free to look through that and kind of understand. But when we're talking about acetic acid in this case, acetic acid is a weak acid, and then when it has its salt, and this would be considered its salt because it's what's left afterwards, it would actually resist the change if I added a strong acid or a strong base to it. So that brings us to water. Earlier in the first lesson, we remember that water could act as an acid or a base. We call that, why can't I remember to do that? We call that amphoteric. So that's the second time you've seen that definition. Having some, let's just start that page over. Which means it can act as an acid, I cannot talk, an acid or a base. Okay? Water also has the ability to do something called auto-ionize. And we kind of showed you that earlier. When you have water, what you actually have is you have HCO plus is in hydroxide. Okay? And in neutral water, remember water is neutral when it's pure, those values are equal to 1 times 10 to the negative 14. And so if you took the negative log of that, you would get 14. And that is where we get that pH plus POH is equal to 14. Okay? So because of that, in pure water, pH is 7 because this is its value. Okay? And so that's going to take us to indicators, which we have to talk about before we talk about titrations. Indicators are chemicals that change color either in the presence of an acid or a base. They're actually weak acids that change because they're either gaining or losing that hydrogen when they're a weak acid. These are some common ones. This bromethymol blue is what we're going to use in our titration. It's blue in the presence of an acid, and then it turns yellow in the presence of the base. Some other things are fruits and vegetables and flower petals can also act as indicators. And this is some of those things we're talking about. And just to kind of show you, you do not have to know the colors. I just kind of want you to see what some of them do and the different pH levels that they change at. That's just a picture of hydrangeas in the presence of an acid. So the soil is acidic, they're bright pink, and if the soil is basic, it's blue, and if the soil is neutral, they're actually purple. So you can actually change the color of your blooms by changing the pH of your soil. Neutralization reactions is the last thing that we're going to talk about for these notes in titration. So this is neutralization, and basically when we react an acid plus a base, we get a water plus a salt, and that's this down here. Salts, of course, are not just NaCl. They're an ionic compound composed of the cation from the base and the anion from the acid. Okay? And, of course, we just need to know when a strong acid reacts with a strong base, we produce a neutral salt in water. So this resulting solution will be neutral. And then here's a couple of examples. Whoops, sorry about that. Went way too far. So, of course, this is water, HOH. This is the salt. And then this is the salt as well. Okay? For titrations, I will end this lesson and finish that on the next one.